Okay, welcome back. This is section 3.3. We're going to talk about analyzing graphs of polynomial functions. By the end of this video, you should have a good understanding of how to graph a polynomial function, as well as how to use a graph or the equation to describe the key features of a polynomial function. So you're going to need graph paper here. First, let's go ahead and talk about some key features. So, of course, we're going to talk about the end behavior of the graph. We're also going to talk about the symmetry of the graph. Remember, even symmetry is symmetric about the y-axis. Our odd symmetry is reflected about the origin, so around the origin. We also have the degree of a function. So that's a value, but we can also describe it as an even or odd degree, which is not the same, but is somewhat connected to symmetry. So when we say something is even symmetry, then it's probably an even degree function. But if we say it's an even degree function, that doesn't necessarily mean it's going to have even symmetry. So we want to make sure that we are fully explaining what we're talking about. We are, of course, going to talk about domain and range, and then extrema, so absolute and relative maximums and minimums. We're also going to talk about our x and y intercepts, our zeros, our increasing and decreasing intervals, and then, of course, the turning point, so when it starts to increase or when the graph stops increasing and begins decreasing, or vice versa. We are going to talk about when the function is positive or negative. Okay, so let's do our first example. So the first thing we're going to do is we're going to talk about end behavior because we can get a lot of information from that leading term. In that leading term, we know that is a fourth degree polynomial, right? It's raised to the fourth power. So that means it has, it is an even degree polynomial. So that doesn't necessarily mean it has even symmetry, but it is an even degree polynomial. And so that means that the behavior is going to be the same as x goes to negative infinity as it is when x goes to positive infinity. And the fact that the a here is negative means that it's reflected over the x-axis. So that means our behavior, we can kind of think of it as down, down. In other words, as x goes to negative infinity, y is going to go to negative infinity, and as x goes to positive infinity, y is going to go to negative infinity. The next thing we can look at is our y-intercept, because that's easy. We can put 0 in for x. And so when we do that, we know that if x is 0, then this term is 0, and this term is 0, and this term is 0, and this term is 0. So we end up with f of 0 equals 1. So that's our y-intercept. Okay, to get our other points, we're going to make an xy table. So we go ahead and make a table of values. And since I know f of 0 was 1, I already know 1 point, so I know 0, 1. So I'm going to go ahead and write 0, 1 here. Now, up until this point, we've been able to get away with getting a pretty decent picture of the graph using integers. In polynomials, though, we really kind of want to find what's happening in between those integer values for x as well. So I'm going to go ahead and find some y values for half intervals. So negative 1/2, negative 1, negative 1.5, negative 2, as well as 1/2, 1, 1.5, 2, and we'll see if we get a good picture of the graph here. So go ahead and pause this video and find the corresponding y values, and when you come back, we'll confirm that we have all calculated them correctly. Okay, so when x was negative 2, we find out that y was negative 15. When x is negative 1.5, then y is negative 3.75. If you're not getting the correct answers, please remember that order of operations tells us that we need to do exponents before we do multiplication. So we're going to do x to the fourth, Then we're kind of multiplying by -1 here. We're making it negative. And then we continue on through. Okay, so when x is -1, y was 0. When x is -1/2, y is 6/10. When x is 1/2, y is 2.8. When x is 1, y is 6. When x is 1.5, y is 9.1. And when x is 2, y is 9. So before we start graphing, let's take a look at this table. When we look at this table, it looks like we have very low values for y, which makes sense because remember, we're going to start down and come up, right? Because we said as x goes to -infinity, y is also going to go to -infinity. So we're kind of coming up, right? And then it looks like we get to a point where our graph kind of hits a peak. And here where y values are increasing and increasing. And here we go. So y hits a peak, right? And then it looks like the graphs start coming back down. So let's go ahead and graph some of these points and take a look at what's happening. Okay, so when we were at -2, we were all the way down off the graph, right? So our graph is going to come from below. And then at 1.5, we're at -3.75, so we're about here. And then at -1, we're at 0. And at -1/2, we're at 0.6, so right about here. And then at 0, we're at 1. And then at 1/2, we're at 2.8. And then 1/6. And then 1.5, 9.1. And then 2.9. And so I can see that my graph is coming up and then turning, and it's going this way, but I'm not sure what happens after 2. So let's go ahead and find what happens at 2.5 and at 3. And I'll go ahead and pause. You go ahead and pause the video and find those values. Okay, so you should have found that when x is 2.5, y is 1.3, and when x is 3, y is -20. Okay, so 2.5 is 1.3, and then 3 was all the way down here at like -20. So the graph is going to come up and then turn around and come straight back down here. And again, we don't want to cross over 3 because 3 goes down to -20. Okay, so the points that I have put an arrow at here, you can see this was kind of the high point, right? The y values on either side are lower than this. So this is a good indication of a maximum. And when we look at our graph, we can tell that this is going to go down forever and this is going to go down forever because of our end behavior. So if this graph is never going to come back up again, that means that this is an absolute maximum. Now, this might not necessarily be the exact absolute maximum. We might actually have to put this in a calculator and calculate the absolute maximum. And in calculus, you'll learn ways to find the absolute maximum from the graph. But for now, we're going to estimate the absolute maximum on a table by looking for values that are higher than the y values next to them. And on a graph, we would look at the point that is highest. So when we look at this, the absolute maximum occurs approximately at 1.5. And so looking at this, it looks like the absolute maximum is 9.1 at 1.5. So if we want to talk about the domain here, that is all the x values. This graph looks like it's going to go to the left forever, and so as we go in, and we're going to go all the way across, and as we go down, it looks like it goes right forever. So the domain is going to be negative infinity to infinity, but the range here, we can look at the absolute maximum as kind of the height of the range. And so we can estimate the range that goes down forever. So from negative infinity, and then it's going to come all the way up. So I'll use my mouse here so you can see. The range is going to come all the way up, and we have y values all the way up until we get to here, which we said was approximately at 9.1, and that includes 9.1. Now again, if we wanted the exact range, we could go ahead and use a graphing calculator to calculate that, or we could pick some more points right around 1.5, so maybe 1.4 and 1.6 to find more exact values. We also notice that we have our y-intercept right here. Our y-intercept is at 0, 1. And we have two x-intercepts here and here. We have an x-intercept at exactly negative 1, 0. And then we have another x-intercept that looks like it has to be a little past 2.5, because remember 2.5 we already found is 1.3. So we can estimate that maybe 2.60. So we have a y-intercept at approximately 2.60. Okay, go ahead and try this one. If you want to pause the video right now, and we'll be right back. Okay, so hopefully you went ahead and made a table of values first and talked about the end behavior a little bit, found the y-intercept, and then created your table of values. If you do not want to see my table of values, please put your hand over the blue square right now. If you do want to see the table of values and double check to make sure that you're correct, I'm going to show them right now. Okay, so if you want to see the table of values, go ahead and pause the video, take a moment to do that, and I'll show you the graph in class. Everyone else, let's go ahead and try example 2 so you can take your hand away. Okay, so example 2, we want to try to figure out where our real zeros are. So with every graph, we go ahead and start off with looking at the leading term, because that's going to kind of give us our end behavior and start to help us get a picture of what this graph is going to look like. We do have an odd degree here. So an odd degree means that our end behavior is going to be in opposite directions. So either x is going to go to infinity and y is going to go to negative infinity, and then going the opposite direction, y is going to go in the opposite direction than it did before. So in this case, we have a positive a, so that means if x is negative, so as x goes to negative infinity, it's going to be cubed, so it's going to keep its negative, so y is going to go to negative infinity, and as x goes to positive infinity, y is then going to go to positive infinity. Okay, so let's go ahead and make a table of values. So first value I want to look for is always the y-intercept, because that is simple to find. So if I put 0 in for the x's, I'm going to end up with 0 in my first term minus 0 in my second term plus 0 plus 1. So my y-intercept is 0, 1. So I'm going to put that here. And then again, I'm going to try to pick some half values so that way I can get a good picture of what my graph looks like. And I'll take it out to 2, and we'll see if we need more. So go ahead and pause the video right now and try to find some corresponding y values for those x values. Okay, so when x was negative 1, you should have found that y was negative 7. When x is negative 0.5, you should have found that y is 0 or 1.6, negative 1.6. At half, y is 1.6. At 1, y was 1. At 1.5, y is negative 1/10. At 2, y is negative 1. And so when we want to find zeros, if it's a real zero, then we want to look at where is the graph positive and where is the graph negative. And we can go ahead and graph these points, but let's try to find it from a table first. So when we're looking, it looks like our graph, here our y values are negative, and then it looks like they start to become positive. So if we're looking at where is the graph negative, it looks like as x goes to negative infinity, y goes to negative infinity. So it looks like this graph is going to come in from, if we get more and more negative values of x, we're going to get more and more negative values of y. So our graph is going to be negative from negative infinity up until negative 1/2. And then from approximate, and these are approximate. So it's positive here. It looks like it's positive here until it gets to approximately 1.5. So we're positive from approximately 0 to approximately 1. And again, these are all approximate values. These aren't exact values. And then it looks like it's negative again. But our end behavior tells us that our graph should go off to positive infinity. So it looks like we might need some more values of x to get a good idea of what this function is doing. So let's go ahead and pick 2.5 and 3. Go ahead and pause the video and find those corresponding y values. Okay, so when x was 2.5, y was negative 9/10, and when y is 3, or when x was 3, y was 1. So now we're back in the positives. Okay, so it looks like when our x values go up to 2.5, our y values are negative, and then at here we're positive. Okay, so that means it looks like we're negative again from 1.5 to 2.5, and then we're positive from 3, and then it would go off to infinity because our graph is going to go off to infinity as x goes out to infinity. So our zeros are going to happen kind of at these interchanges. So our real zero, we can estimate that our real zero, and since it says integer values, we can estimate that we're going to have a real zero somewhere between -1 and 0. So 0 between x equals 1 and x equals 0. More precisely, somewhere between x equals negative 1/2 and 0, but it specifically says use integer values. Okay, and then it looks like we're going to have another 0 because here, right, we go from positive to negative. So to go from positive to negative, you have to go through 0. And it looks like that happens between 1 and 1.5. So that's going to happen between x equals -1 here, right? Because -1/2, so -1. X equals 1 and 1/2, but we'll call that x equals 2 because, again, the directions say to use the integers. Okay, and then we cross over again from negative to positive. It looks like between between 2 and 5. So between x equals 2 and x equals 3, we have another 0. Okay, so let's go ahead and graph those points and see if our graph matches up to what we're thinking. Okay, so -1, -7, and -1/2, -1.6, so that's about here, and 0, 1, and 1/2, 1.6, and 1, 1, and 1/2, 1.5, -1/10, and 2, -1, and 2.5, 9/10, and 3, 1. Okay, so that gives us a pretty decent picture of our graph. It comes up, and it goes down, and it comes up. And when we look, we cross our x-axis here between -1 and 0, so that checks out. And then we cross again between 1 and 2, and that checks out. And then we cross again between 2 and 3, so that checks out. So there are zeros. And again, we can see some maximums. So it looks like we have a maximum at about 1.5. So that is a relative max. And we know it's relative because this graph goes up forever. So that's not an absolute max. And then it looks like we have a relative min here at approximately 2, -1. So we can say we have a relative min at 2 of -1. Okay, go ahead and try this one. I want you to do the same thing. Look at the end behavior and then create a table and try to determine where the zeros are from the table and then graph the function to confirm that that's where your zeros are going to be. So I'm going to go ahead and put the table of values up here for you in a moment. So go ahead and pause the video, work it out for yourself. Okay, welcome back. If you want to see the answers, I'll pop them up in a minute. If you do not want to see the answers, go ahead and put your hand over it. If you haven't started the video yet, go ahead and pause it now. Or if you haven't paused the video and tried this problem yet, go ahead and pause the video now so that way you're trying it on your own. Okay, here are the answers. Make sure they're covered if you don't want to see them. Okay, pause the video if you want to jot those answers down and check your answers. Otherwise, let's try another example. Okay, so in this problem, we want to estimate the x-coordinates at which relative maximum and minimum occur. So again, just like all functions, we want to take a look at the leading coefficient, and we notice here that it is an odd degree, so that means that our y values are going to end in opposite directions, and a is positive, so that means as x approaches negative infinity, a negative number cubed is going to stay negative, so y is going to approach negative infinity. And as x approaches positive infinity, a positive number cubed is going to stay positive, so y will approach positive infinity. Okay, so as always, let's go ahead and make a table of values. You'll notice this table of values is a little bit bigger because we're probably going to need a couple more values. The first we always want to see if we can find is f of 0. And so 0 minus 0 minus 0 plus 3 is going to be 3. So 0, 3 is going to need to be a point on the graph. So 0, 3. And then let's go ahead and do what we did before. Negative 1/2, negative 1, negative 1.5, negative 2, and 0.5, 1, 1.5, and 2. And we'll see what kind of information we get from that. So go ahead and pause the video and find those corresponding y values for the x values we just wrote down. Okay, so for negative 2, you should have gotten y equals negative 17. For negative 1.5, you should have gotten y equals negative 6.5, or 4, excuse me. For negative 1, you should have gotten 0. For negative 1/2, you should have gotten 2.9. For 1/2, you should have gotten 1.1. For 1, y will be negative 2. For 1.5, y will be negative 5.6. 5.6. For 2, y will be negative 9. Okay, so we look here and we notice that our y values are negative, and then they are 0 right here, so we know this is a 0 of the function. And then our y values are positive, and they're still positive. So look, this looks like this is the highest y value between those. And then it's 0, so that means we have a 0 here because now we have negative values here, and it looks like they're getting more and more negative. So let's pick some more x values to see what's happening with the graph. So let's pick 2.5 and 3 and 3.5 and 4, and we'll see if that's going to be enough to see what our graph is doing. So go ahead and pause the video right now and calculate those corresponding y values for each of the x given. Okay, so for 2.5, we have negative 11.4. And when x is 3, y is negative 12. When x is 3.5, y is going to be negative 10.1. And when x is 4, y is going to be negative 5. Okay, so even though all of these are negative, we notice we're getting more and more negative, more and more negative, and then we come back up. So that means this looks like this might be a minimum here. And again, remember this we said might be a maximum. But we're not quite at 0. So let's pick some more x values to see if we can find the corresponding zeros where the graph crosses the y-axis. So go ahead and pause the video and let's find some more y values. Okay, so when x is 4.5, we should have gotten y equals 4.1, and when x was 5, we should have gotten that y equals 18. Okay, so now we can see here that these are positive, so that means we had a 0 here. So according to our graph, it looks like we have zeros at x equals -1, and then we have a 0 between x equals 0 and 1, and we have another 0 between x equals 4 and 5. And it looks like we have a maximum, and this will be relative, right, because the y values go from -infinity to +infinity. So we have a relative max at 0, 3, and it looks like we have a relative min at 3, -12. Okay, so let's go ahead and graph this function and see if what we got from the table matches up with what we graphed. So -2, -17 is off the graph. -1.5, -6.4 is going to be about here. -1, 0 is going to be here. -1/2, 2.9 is almost 3, so we're going to go up here. 0, 3 is right here. And then half, 1.1 is just above 1, so we're about there. 1, -2 is here, so it looks like the graph is coming back down. 1.5, -5.6, so that's down here. 2, -9 is all the way down here. 2.5, 11.4 is going to be about here. 3, -12 is right here. 3.5, 10.1 is here. 4, -5 is right here. 4.5, 4.1 is here. And 518 looks like it's off the grid. So I'm going to draw this so that we have the 0 drawn. So it's going to come down and then up and then back down. Okay, so here are my arrows. And it looks like my 0, again, happens at -1, and then between 0 and 1, so that's accurate, and between 4 and 5, so that looks accurate also. And then we said we have a relative maximum at 0, 3. I'm going to guess it's going to happen actually a little bit before it, but that's okay. And then we have a relative min at 3, -12, and there's our graph. Okay, so go ahead and try this one. Again, end behavior, find the y-intercept, and then we're going to use the table to estimate the x-coordinates that involve the relative max and min, and then double check that with your graph. Okay, pause right now and try the video, or try the example. Okay, welcome back. If you want to see the table of values, I'm going to put that up in just a moment. If you do not want to see the table of values, go ahead and put your hand over it so that way you don't see it. Okay, so here's your table of values. Pause the video if you want to check your answers, because we're going to move on to one last example. Okay, in example 4, we are going to talk about end behavior, degree of the function, find the number of real zeros, determine where they are, and then estimate the x-coordinates at the extrema. Okay, so the first two numbers we can certainly, or the first two questions we can certainly find right away, because we know we can use the leading term to decide what happens to the function. So we're not going to make a table of values yet, but for right now, so end behavior. If x is negative, so as x approaches negative infinity, this x cubed is going to stay negative, and then we're going to multiply it by a negative, so that's going to make it positive. So y is going to approach positive infinity. As x approaches positive infinity, a positive number cubed is positive, and then we're going to multiply it by -2, and so that's going to cause y to approach negative infinity. The degree of the function, it is a third degree polynomial, third degree, which means that it's an odd degree, which supports the fact that our y values go off in opposite directions. Okay, so to find the number of real zeros, we're going to want to find some xy values. So let's go ahead and try. My starting point is always -2, -1.5, -1, -1/2, 0, half, 1, 1.5, and I didn't leave space for 2, but that's okay. Okay, so go ahead and pause the video and find your corresponding y values for those x values. Okay, so f of -2 you should have found was 6. That's a 6. Okay. F of 1.5 you should have found was 1/2. F of -1 is -1. F of -1/2 is 0. F of 0 we didn't need to calculate. That's 0 plus 0 plus 0 plus 2. So that would be 2, right? F of 1/2 is 3.5. F of 1 is 3, f of 1.5 is -1, and f of 2 is -10. We'll just fit that right in there. Okay, looking at our table, let's look at where we think zeros might occur. So here we have some positive numbers, and then this is negative, so we know we have a 0 that occurs here, and then this is 0, so that's obviously a 0. This is positive, and this is all positive, and then this becomes negative. So from the looks of it, there's another 0 here. So it looks like we have a 0 so we have zeros between x equals, so this is between -2 and -1, right? So the 0 is happening between -2 and -1. -2 and x equals -1, and between, it looks like x equals 1 and x equals 2, right? And x equals 1 and x equals 2. And then we have an exact real 0 at 1/2, but it says determine the consecutive values between each real 0. So we can say a real 0 at -1/2 because we know exactly where it occurs, or we can say between -1 and 0. So we could also say between x equals -1 and x equals 0, because it does say estimate, it doesn't say give the exact. Okay, and then estimate where the extrema occurs. So when we look, it looks like we're coming down from infinity, and we keep coming down, and we keep going down to -1, and then we come back up to 0. So that looks like this right here is going to be a minimum, because that's the smallest value between the two around it. And then we come up and come up and come up, and then we come back down. So this looks like this is going to be a maximum. So it looks like we're going to have a relative minimum at -1, -1, or we have a relative minimum of -1 at -1. And then it looks like we have another maximum. So we have a maximum at 1/2. So we have a relative maximum at 1/2, 3.5. Okay, so let's go ahead and graph this and see if what we did was accurate. So -2, -6, -1/2, 0.5, 1.5, 0.5. -1, -1 is right here. Oh, +6. Sorry, 2, 6. So there we go. Ignore that point here. Okay. -2, 6 coming down here. -1, -1/2, 0. So there we go. 0, 2, 1/2, 3.5, 1, 3, 1.5, -1, and 2, 10. Okay, so if we're just looking at the pattern of our function, it looks like it's coming down from infinity, and then back up, and then back down, and there we go. Okay, so we said we have a relative maximum around half, and that looks like that's true. There's our relative maximum. And then it said it looks like we have a relative minimum at -1, -1, and that looks correct. And then we said we had zeros between -2 and -1, between -1 and 0, and between 1 and 2, and that also checks out. Okay. Thank you so much for listening. I know this is a long video, so I appreciate you bearing with me. If you need some more examples, go ahead and watch the more examples video. Otherwise, go ahead and complete the 3-3 analyzing polynomial functions reflection. And up next, we're going to talk about how to solve some of those polynomial equations that we've been dealing with.